Hello, I'm Craig Hill with CNA Technology, and today's topic is utilizing the Internet of Things capability, IoT capabilities, to automate production, reporting, quality, and maintenance. So thanks for joining today. I'm out of Indianapolis. I'm an application architect with over 25 years of experience implementing, upgrading, optimizing JD Edwards and other ERP systems. And on this particular project we're going to be talking about today with NTN Dry Shaft, I was the application architecture oversight person advising the steering committee and the functional team on the overall application architecture. And this is for a new manufacturing facility for a tier 1 automotive company called NTN Dry Shaft. And the project was in Anderson, Indiana. So this is a case study type format. I'm going to tell you a story, what we did with NTN at this plant as part of a rollout of JD Edwards Enterprise 192. So NTN makes anything with a bearing in it, essentially, that goes into cars and trucks and some heavy duty, even ATVs. And you can see they'll make needle roller bearings like in a transmission. They'll make CV joints like this joint, basically the shaft that connects the hub to the transmission. Steering column, this is actually a steering column ball joint here, and other components that don't actually make the wheel hubs like this where the wheel hooks on. And here's a constant velocity joint, a CV joint, and other bearings for various applications. So they're about a $9 billion company in U.S. currency. And in North America, they have plants in these locations, sales offices, manufacturing plants, and warehouses. So they're throughout the U.S. In a rollout of JD Edwards. And overseas, they use a different system. So this is a night, kind of a nice picture of the plant at night. It used to be a cornfield in Indiana, just northeast of Indianapolis, and they built a very beautiful plant here. And the purpose of this plant was to do the assembly of continuous velocity joints, basically taking a shaft and connecting it with a CV joint, assembling the CV joint itself. There's different cages and bearings that go into that, and some boots, an inner and outer race, and that's all hooked together. So this plant was built to support requirements for Tesla and for also, I believe it was Toyota. I'm sorry, Honda and Tesla. So this is a little picture inside the shop floor. Very automated assembly lines, a lot of robotics, a lot of PLC. You can see the on-bonds, the red, yellow, and green lights if the machine's running or stopped, or there's a caution, someone just needs to check on it. And there's a lot of mechanics going on in robotics inside the shop floor. You can see it's a Team 4 finishing is what they call assembly. So there's some input and assembly and output coming off the machines. And you can see some of the workstations here. Is a very new plant and built out to support these two customers, automotive OEMs. So the business challenges that we were working on for this plant is to avoid having to do production reporting manually. What's produced off the shop floor, what's consumed. Wanted to make sure it wasn't manual, that it wasn't untimely, and it wasn't inaccurate. So scrap reporting from inventory hold locations had to be timely and accurate, and quality reporting. A lot of the other plants were paper-based, and we wanted to make sure this new plant that it was not paper-based, and it was as automated as can be. And the maintenance activities were really other plants. They weren't integrated with the ERP system, so JD Edwards equipment maintenance or capital asset management was included in the scope, and they wanted to be able to do performance analytics out of the system without having to compile data in Excel, be Excel based for their performance analytics. And they needed good user community, ease of use, and be able to give management operational visibility to the performance of the plant. So this was a smart plant vision, design vision that they had for the plant, for a person to walk up to a work center and to be able to badge in, to check their training certifications against the requirements of what was being built and machinery being operated, to be able to automate the work order transaction and backflush the material based on the PLC count, the programmable logic controller inside the machine, to gather that, because the machine knows how many it's consuming, how many it's producing. It knows the tolerances. There's some built-in quality checking in the machinery, and they want to be able to capture lot serial number for safety, recall, and traceability purposes, similar now in automotive to what's done in pharmaceutical. And to have work order completions, they didn't want it to be fully automated. They wanted to do an RF scan of the completions, but have that kind of validated by the machinery, because sometimes a part would come out and they just need to do a little bit of rework and it would be fine. So they were keeping some manual intervention, and they wanted to have views of the work order instructions, videos, and quality tests, and then also to capture some operational equipment efficiency information, such as when the machine was running and down, error codes, and how much it was producing for the hours that it was operating. So that was the vision. So this is a view of some of the display, like an MES type display on the floor, on the machinery. A lot of lights, and it's a touch sensitive screen here. So you can push on it, but kind of the key to this is there's inlet, how many parts are available. So it actually has a counter here, 73 parts in, no parts in the inlet right now. And then a counter of how many parts are being output. And then this, NG is short for no good. So this is the, if the machinery detected that a part was no good, it spun it, there was too much friction or noise in the unit, it would be expelled from the machine through a no good counter portlet. So it knew how many were being at least initially scrapped, and then the cycle time, how often does a part come out of the machine. So, and you can see the part number it's running, and the employee that's badged in and operating that machine. So we had this cool information. These are equipment run by a Mitsubishi PLC controller, the robotics put together by Mitsubishi. And we had to tie into that machinery to grab some of this information electronically and tie that into JD Edwards via IoT, or Internet of Things. So we wanted to be able to capture the quantities in a super backflush and report that via IoT. So this is a work order completion screen. I'll zoom in so you can see it a little bit better, right? So we have a work order here, 1072 for this part number, the date, shift. We know what branch it's in, and how many are ordered, how many are completed, scrapped, and so forth. So this is the routing. There's a 4-step routing here of going through the work center, just one work center, but a different description as it's processing through there. So this is the PLC count coming in, and we know what employee is logged into JD Edwards here, and we want to know the quantity completed, scrapped, the quantity at that operation. I'll zoom back a little bit here so you can see the whole thing, but not all the way. And so what's going on here is there's 168, the quantity at that operation. There's 48 out of that operation, and no scrap recorded here. And then you can see the status and the pay points here. So what's going to happen here is the information gets updated. So the front door PLC count would be here, and the back door RF scan, this is RF Smart, the RF Smart scan will come in here. And so we know how many went in the machine and how many were scanned out of the machine, and they needed to reconcile and count for all those quantities. How many are in rework, how many in scrap, how many completed, how many have not gone yet into the machine against the quantity that's on the work order for completion. So that's the production reporting, the shop floor control reporting, but also we had the opportunity to capture quality information. I'm going to come in here a little bit closer so you can see this. So there can be different measurements done. This is a test method that the PLC has measured the outside diameter of the stem. It's measured the roundness of that stem. Is it perfectly round, or is it elliptical or oval shaped? And then it's taking the outside diameter of the seal seat and measuring that. So this is, I believe, in microns here, or perhaps it's millimeters down to a micron. And you know, the sample number. So this is the J.D. Edwards quality module. So you can see, you know, it's coming from the daily processing and quality. So we're able to capture automated statistics at the PLC level from the work center on the dates and know what's going on from a quality standpoint. So really, really cool stuff, I think, that we're capturing production reporting, and then also these measurements. And what the design here to fully implement is to see, you know, these are test results. Are those within tolerance? If they're not within tolerance, to create a maintenance work order for someone to go and check that machine out. So it's a condition-based type equipment maintenance. You can go out when there's a problem, in addition to going out every so many days. We also know what's running through the machine, so we can just say every so many thousand units produced, it needs some maintenance of this type. So there's a lot of good information to be able to capture off the machinery, as automated as this were, as this process was. So this is some of the scrap metrics that we're able to generate out of the system, tracking scrap. You know, the dollarization of that scrap, the scrap ratio by month, and various metrics here with percents and quantities and a dollarization of those amounts. And some other dashboard and trending information here, completed parts by day, just this raw production, what's being produced off the line. We now know that, and we know the sensors by work center, what quantities are being produced, and we can see shift totals, what was scheduled to be completed, what was actually completed, and the scrap, and capture that information out of J.D. Edwards after it's captured it from the machinery, and some also from the RF scan after the balance, the totals have been balanced. So pretty good information off the shop floor, so we can know what's going on. So of course, a project like this is not without its challenges. So I always like to, this is the part in the Fixer Upper show where they said, oh, we tore this off and we found this problem behind this wall. So some of we have a few challenges that we list here. An enormous amount of data is available at that PLC level. So the lesson was, just because you can doesn't mean you should. A lot of data that we could capture, but what should we capture? So production reporting at one pay point versus the 4 available. You saw there was a lot more available we could capture, but we don't really want to do that. We got to be kind of careful what you wish for. So the frequency of updating J.D. Edwards transactional data was another point. We decided every 15 minutes to capture a backflush so we don't overload the 4111 CardX file by just pumping massive amounts of data. That's pretty frequent. We saw there's a cycle time about every 60 seconds on that machine. So this might capture a completed quantity of 15 every 15 minutes. So that was the frequency that we decided. So what data do you capture and how frequently do you do it? And also the quality test. How often do you do that? Do you test every part? How often, do you ask the machine for that data? And this was pretty frequent at 30 seconds. So that was some of the be careful what you wish for. And then leveraging IoT to launch data as business functions, but understanding maybe gaps in the data sent. The example, the PLC knows the item and the quantity, but it did not know the JD Edwards work order. So we had to be careful as we're capturing data, did we move from one work order to another? So there was some manual resets to say, okay, JD Edwards, I'm switching to another part. Okay, machine, I'm switching to another part. I mean, the machine has to know, but the operator could forget and tell JD Edwards, hey, I've moved on. So we don't want to capture the next part against the previous work order. So we had to make sure that we had that in sync. Because the machinery doesn't always know everything that's going on. So, and then we had some infrastructure issues establishing the IP address to ensure scalability. It took some doing it wasn't an Allen Bradley, it was a certain very late model of Mitsubishi PLC. So to tie into that, it took a little bit of work to kind of bust the code. It was actually a free driver that we ended up finding that was necessary to make that final connection. So just, some technical challenges. So that's, drilling into that part of the project. This is case study information about the whole project. This is some pictures of what was being produced. It was a 1.2 million square foot manufacturing facility. Some of you are in manufacturing enough to know that's a pretty good sized place. And Anderson project was a greenfield implementation for a newly built manufacturing facility. So we didn't want some of the older facilities to have some of legacy procedures and processes. It was nice that we had a new facility to work in. We said, let's start off on the right foot, do it right the first time. Very, very, very important for the project. So it's a greenfield implementation, IoT, with a smart plant vision. Wanted to leverage. So we did have some good processes at the parent plant, a large kind of mothership plant in Columbus, Indiana. In Indiana, you just say Columbus and it means Columbus, Indiana. But everybody else thinks it means Ohio. So this is Columbus, Indiana. They were running World, and they did have some good practices there. So we wanted to leverage that, but of course, old system implemented 20 years prior, and like scrap reporting was always a problem at that plant. So we wanted to do it better. So we did assessed for opportunities for improvement, implemented JD Edwards, implemented IoT, incorporated the quality, supplier portals, flex accounting, and a lot of the UX1 capabilities. So we did some nice Cafe One type screens for them, and gave them some nice flex accounting that was useful for them. So it was a really successful project. It was timely, accurate production reporting, and we improved inventory accuracy. We were able to capture quality information automatically, improve the analytics, trending, and dashboards. One of the problems you run into, people are looking at weekly, monthly, maybe sometimes daily performance metrics. Well, how do they do that? They get a big PDF report, they take the totals, some data off of that, they put it in Excel, put it in the PowerPoint, and they present it in the meeting. And it's their view of the world, right? Well, what we're trying to get to is, here's data coming off the system. It's raw, it's not interpreted, there's nothing hidden, it's transparent, and it's real time. So you're not looking at what happened last week. You're looking at what happened this week, today, this month. There's no delay in capturing the data. That was the goal that we had for this project. So pretty successful project. We went on and implemented some additional plants after that. So that's the presentation I have for you. Standard, explanation of who Quest is for individuals, for companies. Session ID. Here's my contact information. Doesn't look like there's any questions, so thank you very much for your interest in today's IoT topic and what we did with JD Edwards for the anti-dry shaft. Thank you very much.